So let's start putting this into practice. Remember that when I introduced enthalpy a couple videos back, we used the first law of thermodynamics to get there. We said that delta E was equal to Q plus W. Okay. And then we replaced work W with negative P delta V. All right. So we had looked at this from two different perspectives. We said, what if we hold volume constant? Okay. And then we said, what if we hold pressure constant? Now, I said that it was very difficult for to do this, to do the volume being held constant, but it turns out that we can do it. And in order for us to do it, we have to use something called a constant volume bomb calorimeter. Now, this is pretty sweet. So let's take a look at this. All right, so you've got a container within a container. So let's take a look at the smaller container first. So inside the smaller container, you have a bowl, okay? And that bowl contains the item of interest, okay? That contains your sample. Now, we also have a wire running through that sample. And what's going to happen is that once we start the experiment, we're going to run an electrical impulse through that wire, and basically we're going to heat up that substance. Now, what we're also going to do inside this container, it's filled with oxygen gas. So what happens is that we're gonna bleed out all the normal atmospheric air, like the nitrogen, oxygen, carbon dioxide, all that stuff. We're going to bleed that out and replace it with pure oxygen gas. So that way, when we do send that electrical impulse down through the wire and through our sample, we're going to combust it. So it's like we're doing a controlled explosion inside the mini vessel. Okay. Now, here's what happens, though. When you explode, woo! Okay. So when you explode this, what happens is that the heat from the explosion is going to leak out from the smaller vessel into the water. So the water absorbs that heat. So inside the larger vessel now, you filled it with an amount of water that you know accurately. You know how much water you've placed in there. You know the density of the water, so you can figure out what the mass of the water is. Okay. And what you're doing is actually measuring the heat. You're measuring the temperature change with the thermometer. So the temperature is going up. So if you do this explosion, eventually the heat's going to leak out from the smaller container, because again, that's by definition a closed system, that you can exchange energy, but you can't exchange mass. So all you're doing is exchanging the energy from the inside container to the water, and you're measuring the heat change using a thermometer. So you're watching the temperature go up. All right. Now, the design of the bomb calorimeter allows us to assume that no heat or mass is lost to the surroundings during the time it takes to make the measurements. Because once you're, again, I just to explain, the inside the bigger container, this is completely isolated from the outside. So it's like when we're studying this is your entire universe. Okay. So the heat that goes into the water, that heat never comes out. It stays inside. It stays inside the water. It stays inside your container. Now, because no heat enters or leaves the system, the heat change of the system must be zero. Okay. So if that's the case, then we can say, using the first law of thermodynamics, we can say that the heat of the system is got to be equal to the heat of the calorimeter plus the heat of the reaction. So remember, the heat of the reaction, that's your inside container. Heat of the calorimeter, that's your outside. Okay. So this is your inside, outside. Okay. And this all has to be equal to zero, because that's the first law of thermodynamics. Now, if that's the case, that the heat of the calorimeter plus the heat of the reaction is equal to zero, then we can say that the heat of the calorimeter has to be equal to the negative heat of the reaction, and vice versa. Now, that being said, If we wanted to know the heat of the calorimeter, we could take this heat, okay, and replace it into our, we could actually use that to solve for the heat capacity, C delta T, or QCAT. And so we can solve for the heat capacity if we know the heat of the calorimeter. All right. Now to calibrate the bomb calorimeter, we have to burn a sample with an accurately known heat of combustion, like benzoic acid. That's the standard. And the heat capacity of the calorimeter is then determined. And then once you know that heat capacity, then you can solve some problems. Now, here's the kicker, though. Because volume is held constant, we're solving for delta E. The heat at constant volume is going to be equal to delta E and not delta H. So this is what we're solving for, delta E. So we could have, when we're solving for delta E, it's going to have similar units to delta H, kilojoules per mole. And so delta E is going to have similar units like delta H. The only difference is it's not delta H, it's not enthalpy. We're solving for the internal energy. So let's try this problem out. You have a quantity of 1.922 grams of methanol, CH3OH, was burned in a constant volume bomb calorimeter. Consequently, the temperature of the water rose by 4.20 degrees Celsius. If the heat capacity of the bomb plus water was 10.4 kilojoules per degree Celsius, calculate the molar heat of combustion of methanol. So there's a lot of stuff here that we have to unpack, and let's see if we can do this. So we're told that we have a mass, okay, of 1.922 grams of methanol. So let me make a note here. 1.922 grams of methanol, MEOH. All right. We know that this was burned in a constant volume bomb calorimeter. So right off the bat, we're looking at delta E and not delta H. And we know that the heat is being held at constant volume. All right. Consequently, the temperature of the water rose by a positive 4.20 degrees Celsius. So we know that delta T is equal to plus 4.20 degrees. Okay. So we got that. If the heat capacity of the bomb plus water was 10.4 kilojoules per degree Celsius, so we know that capital C, the heat capacity, is 10.4 kilojoules per degree Celsius. Okay. We want to know what is the molar heat of combustion of methanol. In other words, what is delta E? So we're looking for a unit for delta E. The unit's got to be kilojoules per mole. That's what we're looking for. All right. So we know C, we know M. All right. We know delta T. We know we're looking for delta E. All right, so here's our possible idea. Since we know what C, the heat capacity, and we know delta T, we could solve for the heat of the calorimeter by using the heat capacity times the change in temperature. Okay, so we can get the heat of the calorimeter. Now, what we can do after that is to use the first law of thermodynamics. So we can say this, that remember up here we said that the heat of the calorimeter plus the heat of the reaction is equal to 0. And so the heat of the calorimeter has to be equal to the negative heat of the reaction. So we could use the first law here. And we can use that to solve for the heat of the reaction. All right. Now the heat of the reaction is going to be given to us in kilojoules. We know the mass of our stuff. So if we were to convert that mass from grams to moles, and then take our kilojoules, the heat of the reaction, divided by moles, by definition, that's kilojoules per mole, and that's what we're looking for. That's delta E. All right, so first step is that we're going to solve for the heat of the calorimeter using QCAT, okay? Second step, we're using the first law of thermodynamics and help us get to the heat of the reaction. And then the third step, take the heat of the reaction and divide it by the moles. All right, so let's try this out. So I'm going to do my work over here on the right-hand side. So heat of the calorimeter is equal to heat capacity times delta T. Well, the heat capacity is 10.4 kilojoules per degree Celsius. Delta T is going to be 4.20 degrees Celsius. So 10.4 times 4.20, that's a zero, that should give us 43.68 kilojoules. All right, so that's the heat of the calorimeter. All right, so the second step, and let me make it number one. So second step, we're going to use the first law of thermodynamics that says this. The heat of the calorimeter plus the heat of the reaction is equal to 0. Okay, now if I rewrite this and solve for the heat of the reaction is going to be equal to negative heat of the calorimeter. So since we know what the heat of the calorimeter is, which is 43.68 kilojoules, the heat of the reaction has to be equal to the negative heat of the calorimeter. So the heat of the reaction is a negative 43.68 kilojoules. All right. Finally, step 3. We know the heat of the reaction is negative 43.68 kilojoules. And if I divide this by the mass of methanol, you've got 1.922 grams of methanol. Okay. If I convert this from grams to moles, if I know that molar mass, and that molar mass is about 32 grams of methanol for every 1 mole, so that way the grams of methanol cancel out, I should have, this is going to be negative 43.68 times 32 divided by 1.922. That answer should come out to be negative 727.24 kilojoules per mole. And so that's how we would do this problem. All right, so that's holding the volume constant. What if we hold the pressure constant? So another type of calorimeter that we could use is called a constant pressure calorimeter. This is used in non-combustible reactions. This is also called the coffee cup calorimeter. So how this works, way back in the day when styrofoam was, plentiful, what we did was take 2 styrofoam cups. Inside the second styrofoam cup, what we did was put our reaction mixture. We put a stirrer in there. We also put a thermometer. And so once we mix our 2 solutions together, we measure the change in heat, we measure the change in temperature, and using that, we're able to calculate the heat of the reaction. Now, because the pressure is constant at 1 atmosphere, the heat of the reaction is directly equal to the change in enthalpy. So remember that that was one of the conclusions that we made. The heat, if it's at constant pressure, is equal to delta H. And so this time when we calculate the heat of the reaction, this is going to be equal to delta H and not delta E. Okay. Now, different types of reactions can actually be studied from this different calorimeter. So we can take a look at heat of neutralization, heat of ionization, heat of fusion, vaporization, as well as the heat of the reaction. All right, so let's try another problem. This is going to be a good thinking problem. All right, so here we go. You have a 30.14 gram stainless steel ball bearing that has a temperature of 117.82 degrees Celsius. It's placed in a constant pressure calorimeter containing 120 milliliters of water at 18.44 degrees Celsius. If the specific heat of the ball bearing is 0.474 joules per gram degree Celsius, calculate the final temperature of the water. Assume the calorimeter to have negligible heat capacity. All right, so we got a lot of stuff to unpack in this problem. So there's 2 things that we've got. We've got a ball bearing, and then we've got a cup of water. Okay, so let me draw that. All right, we got a cup of water sitting on a table. All right, so we need to put this ball bearing inside this cup. Now, keep in mind that the mass of the ball bearing is equal to 30.14 grams. The temperature, the initial temperature, is 117.82 0.82 degrees Celsius. Okay. Now, if we actually know the volume of the water, which is 120 milliliters. Okay. Now, if the density of water is 1 gram per milliliter, that gives us 120 grams of water. Okay. All right. Now, we also know that the initial temperature of the water is 18.44 degrees Celsius. So what's going to happen here is that if we take our water, if we take this ball bearing and put it inside this cup, all right, the temperature of the ball bearing has to go down because that heat is going to be transferred from the ball bearing to the water. The heat that the water is going to get, that temperature, the final temperature, we expect that to go up because you're putting this hot object inside the water. The water is going to absorb that temperature, absorb that heat. Temperature's got to go up. Okay. So what we want to know at the end of the day, what is the final temperature? What is the final temperature of both the ball bearing and the water? Okay, so we're going to be solving for the final temperature. But in order to solve for that, we've got masses of both. We've got the initial temperature. We need a little bit more information. So it would also help if we had the specific heat of both of these. All right, so if we looked up the specific heat of the stainless steel ball bearing, that specific heat should be about 0.474 joules per gram degree Celsius. And I just got that off the table up above. The specific heat of water is 4.184 joules per gram degree Celsius. Okay. Now, here's the thing. Because the heat that's being given off of the ball bearing, that's going to be a negative heat. So Q would actually be negative. The heat, because the water is absorbing that would actually be a positive value. Now, because the heat is being transferred from one space to another, really the heat is going to be equal. It's just one's going to be negative, one's going to be positive. So, in other words, what I'm saying is this. You're going to have this Q of water, Q of the ball bearing is going to be equal to mass of the ball bearing times the specific heat of the ball bearing times delta T. And we know over here on the right-hand side that the heat of the water is going to be equal to the mass of the water times the specific heat of water times the change in temperature. All right. So even though one of these is negative, we're using the same equation. The heat is going to be transferred from one to the other. So they're going to be equal to each other. So that being said, we can what we're going to do is have both equations, but what we're going to be doing is solving for TF. So eventually, we're going to have to combine both sides. We're going to have to combine like terms. All right, so I'll tell you what, we got a lot of stuff here. Let's start popping some numbers in. Hopefully this will make a little bit more sense. So we know that heat of the ball bearing is going to be negative. So let's take care of the left-hand side. So I'm going to put a negative, and I'm going to put the left-hand side in brackets so that way that negative sign doesn't get lost. So we know that the mass of the ball bearing is 30.14 grams. We're going to multiply that by the specific heat, 0.474 joules per gram degree Celsius. Okay, and we're going to multiply that by the change in temperature. So TF minus 117.82 degrees Celsius. Okay, so that's the left-hand side. This is going to be equal to the mass of the water, which is 120 grams, times the specific heat of water, which is 4.184 joules per gram degree Celsius. Okay, and then we're going to multiply that by delta T, TF minus the initial temperature, 18.44 degrees Celsius. All right. So now what we're going to have to do is multiply the mass times S together on both sides, okay? So if we multiply these two, we're going to get a number in front of the third set of parentheses, and then we're going to distribute that. So we're going to get TF on both sides of these equations, and then we got to add it together. All right, so this is where it's going to start getting a little bit ugly, but hang in there. We're gonna get through this. All right, so let's do the left-hand side first. 30.14 times 0.474 is going to give you 14.28. And we're going to multiply that by TF minus 117.82. Okay, so that's the left-hand side. This is going to be equal to, if we multiply 120 times 4.184, this will be 502.08 times TF minus 18.44 degrees. All right. Now, to keep things also simple, because things are going to get a little bit messy on the paper, I know the units. I know where the units are coming from. I'm going to drop the units temporarily, so that way we can just get to a simpler equation, and then we'll go from there. But keep in mind that the final temperature, the unit of our final answer, is going to be in degrees Celsius. All right, so now what we're going to do is multiply everything by, on the left-hand side, we'll multiply 14.28 times TF, and then 14.28 times negative 117.82. We're also going to take care of the brackets this time. So we're going to try to get rid of this bracket, so we're going to multiply the negative sign together. So negative 14.28 times TF, okay, so that would be negative 14.28 TF, a negative 14.28 times negative 117.82, so we're going to add at this time 1682.47. So that's the left-hand side. We're going to do the same thing on the right-hand side, except we don't have to worry about the negative sign because everything's positive. So that's going to be 502.08 TF, 502.08 times negative 18.44. So this is going to be minus 9258.36. All right, we're getting there. So now what we're going to do is start combining like terms. Okay, so we need to figure out how to get all the TFs together. So if I subtract both sides from 502, I'm going to get a really negative number on the left-hand side. What I'm going to do instead is add 14.28 TF to both sides. So that way it cancels on the left. I'm going to get 1682.47. 1682.47 on the left. This is going to be equal to 502.08 plus the 14.28. That's going to give us 516.37 TF minus 9258.36. All right, so now this is a normal algebraic equation. And what I'm going to do is I'm going to keep writing this down over here. All right, so now what we need to do is solve for TF. So we're going to add 9258 to both sides. So we get 516.37 times TF is equal to, if we add 9258.36 to both sides, we get 10,941.60. And if we divide both sides by 516.37, TF ends up being 21.19 degrees Celsius. And there it is. That's our final answer. So what that means is, going back to our figure, you take this ball bearing that's 117.82 degrees Celsius, you put it in 120 grams of water that's set at about 18.44 degrees Celsius. The ball bearing cools down and gives off, the temperature of the ball bearing goes down quite a bit to 21.19 degrees Celsius. The temperature of the water, on the other hand, goes up a couple of degrees to 21.19. And there it is.